right, let's get started. So this is welcome to afternoon session. We have 3 talks in this session. The first one is invited, and then we have 2 other contributed talks. The first one is from Dr. Wang, who currently serves as director of Ion Beam Materials Lab, and also is jointly appointed at CINT at Los Alamos National Lab. He also serves as editor of Nuclear Instruments and Methods in Physics Research. And today he'll talk about ion beams to advance fusion materials research. Okay. You may have to stay very close to it so that we can record. Yeah. So just stay very close to it.
Good afternoon. Thank you very much.
5-minute mark. That's fine.
Thank you very much for the chance to talk about research we're doing in Los Alamos. The title is Ion Beams to Advance Fusion Materials Research. We have heard some talks in the morning regarding some background regarding fusion, what's happening. So some of the slides I have probably just move faster as supposed to be. So many people know where Los Alamos is. In case you don't know, we're a pretty remote area near the Santa Fe of the New Mexico. We have currently have 18,000 workforce in Los Alamos, and the town site is only 20,000 people. So you can imagine many people don't live in Los Alamos. I guess if you don't know Los Alamos, you do know the Oppenheimer through the movie there. So Los Alamos' mission, obviously including stockpile stewardship and global security, the research and also energy research, security research there, are supported by 6 capability pillars. One of the pillar where I'm working with the materials for the future, and obviously under each of those pillars, we have a specific focus areas we're working on. So there is a signature of science of signatures, the nuclear particle futures, like high energy physics, nuclear physics, and the weapons system, complex natural and engineered systems, as well as the MI and the MLAI focus in the information technology area there. So here is the outline of my talk. I'll give a few slides about motivation, why we're working on this. Then we move to some specific challenges related to the fusion. I focus obviously more on the material side, but there are a lot more challenges for the fusion energy to be realized. Then I will give a few slides regarding how the accelerated ion beams help advance the fusion research in terms of materials R&D, and I'll give some specific examples that my team has been working on in collaboration with other groups. With a quick summary. So we're facing unprecedented challenges in terms of energy demand. We Americans use a lot of energy. Those energy sources can come from different ways there. You could have natural gas, or you could have coal and oil. And here we don't have a fusion because we don't have fusion energy yet. But we do have a fission. 1 ounce of fission uranium ore can produce enough energy for us to use per day. So there is a projected energy gap, demand versus whenever we can produce. It's huge. This slide's quite old. It's 10 years ago. Somebody in Los Alamos has come up with some kind of estimate to do this. But imagine if just for 10 terawatts power we need. Current state of art for nuclear power is 1 gigawatt. So we really need many new plants just from a nuclear perspective to fill this energy gap, need a demand gap there. Obviously, clean energy trying to be alternative to the fossil fuel has been around for quite a while, and whether it's nuclear or the hydro or the wind, solar, and so forth. So this is the latest summary about the energy production. This is mainly just for electricity part of it. And there are a lot of changes. But this change, if you look at the ratio of the clean energy versus the total energy we need, it's actually not increased much. But the energy demand has increased significantly in the last 20 years. But this mix, even though we have put a lot of focus on the clean energy, but this change has not been very significant. It's just a few percent there. So that's where the people start to think about even the, undeveloped nations still think about nuclear as the alternative source in addition to the wind solar to make up the gap for the fossil fuel part of it. But most of them are still under development. And so many things had happening, but none of them are big enough. For the longer term, obviously, we come back to the fusion. Fusion has been around for many decades. It's always, another 30 years away when we're talking about fusion in the past. But people think this time might be closer. So there's some, information you can find from a DOE website about the fission fusion comparison. Just very quickly, one is trying to split atoms, produce a lot of energy per fission, but only have smaller energy for neutrons, either 2 or 3 neutrons per fission events there. But fusion is trying to put light elements together, make it bigger, and only produce 1 neutron, but has a lot more energy, 14 MeV. So if you think about the per unit mass, perspective, fusion is going to be 4 times more efficient than the fission to produce electricity. Now, that's not the only advantage. Another advantage is obviously we have much less byproducts. That's where the nuclear waste, we're concerned with the fission part of it. And then obviously the fuel itself. So we got abundant fuel, the seawater for the deuterium there. So there is, this international cooperation happening since 2006, and trying to build the first, international thermonuclear experiment reactor, ITER, is still under construction. Unfortunately, this has been keep delay. It's supposed to be this year. They're going to have a DD neutron at least a reaction, but it looks like it's delayed by another decade. So they just to show the whole difficult the process, obviously there are some other factors cause this delay. So this is the cross-section of this tokamak. And by the way, any energy, we're talking about here for fusion is going to be magnetic confinement. Not the the initial confinement part of it. So my focus is on this part of it. So we can go back to look at that. But in the last 2 years, things really has been taken off on the fusion side. So obviously JET, this is the joint European torus, the tokamak. Before shutdown, it generated the record energy with a very tiny amount of DT fuel there. So then, obviously, NEAF has been mentioned this morning, 2022. There was a breakthrough in the scientific research, it's ignition there. But even just, last year, that specs has been improved significantly. This is how much energy generated from the fusion here compared with how much power put in for the laser part of it. Now, in terms of confinement itself, plasma physics part of it, Chinese Easter reactor has break its own record, continuously. This last month, get to 15 minutes for this is for the high confinement plasma mode, which is needed for generating the energy there. So all those are fantastic news in the scientific adventure area. Also, there are lots of private money put in for the fusion in the last few years. Most of them are in the US. And that's spread out a lot of industries, private companies to work on the fusion concept. The biggest one right now is Commonwealth Fusion System in the Massachusetts there. On the government side, DOE also has changed its focus area from traditional plasma a nuclear plasma part of it, plasma size, into more on the nuclear energy, plasma energy, diffusion energy, and also the materials perspective. So this is the latest, this material-centric, 6 fire centers has been awarded. This is innovative, the fusion engine research there. So all those are great news, and for the fusion, the energy development part of it. So what are the challenges really? So if we go back to this cross-section of the tokamak, confinement here, so there is a tremendous heat flux, particle flux, the neutrons bombard on that first wall behind its structural. Then you have a blanket which you really use to sustain fusion. You have to produce your tritium there because there is not much tritium available in the world. Then there are the shield, the obvious vacuum vessel there, as been mentioned this morning. Just very quickly about this PMI interface, plasma material interface. It's going to be very, very messy. There are lots of things happening during these interactions. And you have ion transport, you have energy transfer, you have materials recycling, you have structural damage on those. So in the end, there are many challenges, and also those challenges may not act alone. Some of them may have a synergistic effect there, which we don't even know yet. So that's for the plasma fission material, which is unique to the fusion. And the fission does not have that kind of unique challenge there. But for the structural material, we can learn a lot more from fission, especially Gen 4, Gen 3 reactors there, because we are temperature-wise, actually some of the fission reactor is going to be higher than the fusion. Oops, it's just keep going back there. Anyway, this is just to show quickly temperature versus the displacement damage. This has been mentioned this morning, is how often that lattice atom has been displaced by the energetic interactions there. So those defects, basically, when they produce those Frankel pairs, most of them actually recover and cause no damage. So we call the healing of the lattice there. But some of those do not recover. They actually form much more complex, irreversible defects into the system. Those are the ones to cause the materials degradation. And obviously there are ways you can mathematically or physically try and describe from how fast those defects generate and how fast they might recombine, cause nothing impact, or how fast they may actually get lost through the other sinks there. So those ultimate response materials to irradiation damage is going to be depending on those fates of the defects there. In reality, this is a very complex process. It's the multi-length time scale and the length scale phenomena. So you start with very low end here, atomic level, picosecond, and you have primary defects production. And then you have a gas production because fast neutrons produce anaerobic reaction, NP reaction. You produce helium, you produce hydrogen. And then those defects recombine or they clustering and they migrate. And then gas can diffuse. It can be trapped in the other defects. They continue to redistribute those and move around. And in the end, you have this nano micro structure and the local chemistry get changed in this one cascade process there. But this is not act alone. And when you have microstructure already in the system, they can impact how this cascade evolves. On the other hand, they can also, this irradiation conditions, like fission versus the fusion, and also the materials property can affect how those primary events are generated in the first place. So there are obviously books you can get into more detail about fundamentals. Some of them focus on the helium effect there. So just a quick summary about for the structured materials, and many of those are similar in the fission system, advanced fission Gen 4 reactors there, but some of them are unique, especially the helium embrittlement in a high temperature because of high production of helium in the fusion system compared with the other system there. But end result is can be catastrophic, so if we don't care for it. So this is just quick summary about what people have mentioned, what the challenges are for the materials, even just a decade ago. I don't think any of the challenges has been, changing much there. First one is, is there a viable diverter and the first wall material actually working for the demo? So demo is the another demonstration reactor between ITER and the real power plants. So the different countries have different versions for it. And, another one is, can the suitable structural material be developed for the demo? And so I think there are some concerns about the advanced fusion plus the structural materials with embedded nanoparticles, which enhance radiation tolerance. But how those nanoparticles becomes the trapping site for the tritium retention. So that's another issue there. That's a new issue. And some of the I guess strategy may need to be reconsidered there. That's the basic challenge on the material side, but there is also challenge on the materials testing side. We don't have anything available to do fusion prototypic testing if we do have materials. So there is this impacts is under development in the Oak Ridge for probably almost close to 5 to 10 years and still ongoing. This is going to test the plasma phase material, thermal testing, particle testing there. But there is no neutrons, no radiation damage part of it. So radiation damage, facility, DOE is trying to propose this fusion prototypic neutron source. This is still on the paper. Even if we have a decision to make, this is a decade away, we have this one. So we have a long way to go in terms of materials testing part of it. Obviously, there are some neutron capabilities available in Los Alamos, in Oak Ridge for the spallation neutrons, but there are some concern regarding the spectrum impact because the much high energy neutron in the spallation neutron source and also much high yield gas production of the hydrogen helium. They're not very typical to the 14 MeV neutron there. So how can the ion beam help? So obviously, it's depending on how we use ion beam in the materials process. Ion beam has been around for a long time. Hey, Michael, how are you? So you can look at ion-solid interactions through Monte Carlo-based approach, and or look at the defects part of it with the MD, material dynamics, molecular dynamics there.
You can also shoot the ions into the solid.
Right, you can also to change the box of the sandbox there. So this is just to give you a quick summary how this transport, ion transport works there. You can look at how deep ion will go, how much energy partitioning into the electrons, how much energy give to the lattice there. The lattice part is where it produces the permanent displacement damage there. So in the end, obviously we can use ion beam as a tool to do the analysis like electrons, X-rays, or we can change chemical composition. Or in this case, mainly we use as a radiation source. I'm going to skip this because I'm going to use one of the techniques here to look at the tritiums. That's why I have this slide. This is basically a very fundamental ion beam analysis approach here. You might ask, there are so many other surface techniques available for the electron beam or for the X-rays. What heck the ion beam does here? Well, for the certain elements, especially interested for the fusion, hydrogen and helium, those are very difficult elements to analyze with other techniques. But ion beam techniques has unique niche on that. I will show that. One of the strengths, most quantitative way without use of standard. You don't need the sample preparation pretty much because all the fundamental physics has been solved a long time ago by those laureates. So, ions are not neutrons, obviously. So their spectrum is different. So, but we use this DPA as a measure again, as the commonality to trying to merge them together. And we use the multiple ion beams to mimic the neutrons, to mimic hydrogen, to mimic the heliums together. So there are, I'm going to skip that one. There are certain things, obviously, certain physics, and the ions just cannot do it, even with 2 beam or 3 beam together. So this just gives you some of the property versus the physics. Some of those blue dot with the white background is the phenomena you can actually do a better job than other places. There are certain areas you just have no way to do anything. This is based on the triple beam workshop we had in Livermore actually a long time ago. So, give you a couple examples. There are a number of ion beam capabilities available in Europe and South Clay, and also in Michigan, and also in the Argonne National Laboratory with ion beam coupled with the TEM there. What I'm talking about here is a very moderate facility in the Los Alamos, and we have 4 accelerators and with 9 beam lines, and the tandem implanter. There's a 9 implanter with a coupled beam line with the tandem. Good thing about this capability, you can access through this user platform we call the CINT, Center for Integrated Nanotechnologies. This is one of the nanoscience centers DOE has. A free access once you write a 2-page proposal, get it funded. And this is center is obviously one of the 5 nanoscience centers in the US. So let's look at the plasma phase material. Obviously, because of harsh conditions, the first people think about is tungsten because that's the highest melting point, and excellent thermal conductivity, and also very low tritium retention, low sputtering rates there. So we're talking about those 3 things interact with tungsten basically now. ITER was designed in the beginning with the carbon as the plasma phase material. Then we very quickly realized that if you use the carbon, those tritium is going to form a methane and will be used up, trapped into the carbon very quickly. And depending on how many shots, this is for the number of 400-second ITER discharge, and the retention of tritium, this is the limit here for the safety. 700 grams in the material there. You can only do 15 hours with carbon wall. You probably don't do many experiments. So quickly change it to tungsten. Now everything is tungsten. And so you can extend to 100-some days for the experiment that you planned for the ITER there. Now issue comes very quickly. Yes, tritium retention rate is pretty low in tungsten, but that's the non-damaged tungsten. Once you have a neutron damage in the tungsten, you produce a lot of defects. Those defects becomes trapping sites for the tritium. So quick, even very little damage, the retention rates jump order of magnitude there. So that's the challenge number 1 with tungsten. So obviously, there are not, as I mentioned, there's not neutron capabilities available. So we use ions to mimic that displacement damage. We use the copper because copper is very easy to produce with our source. We can produce a lot of spotted copper there. You can do single energy, you can do multiple energy to get flat damage profile to mimic the damage of the neutron better. So after the damage, you can look at the thermal conductivity. We had to use a very surface technique, a 3 omega approach, to look at the thermal conductivity change on the in the damaged tungsten, because the ion damage range is relatively shallow. And you can see even with very little damage, about 0.2 dPa, this thermal conductivity drops about more than factor of 2 there already. And even we trying to use a different temperature, do the radiation, but the damage recovery was not significant, just because the tungsten is so high temperature material. We have to go much higher to be able to remove the damage. How am I doing with? Okay. So you can also couple different beams together, and so you can have a non-damaged region, helium damage only, tungsten damage only, helium plus tungsten together, and then you can look at the nano-indentation for this kind of the wafer. This is the pure tungsten wafer we start with, and look at the strength yield change. Look at the hardness, change as a function of the damage there. The quick summary here is this special impact of helium is quite significant. And in this case, even with a little bit of helium there, we are, increase this hardness significantly whenever that bubble formed as the blocking of the dislocations by the helium bubble there. Now, go back to the tritium side there. So there is a very beautiful reaction people use, either ways. You can use deuterium to analyze the helium-3, or you can use helium-3 to analyze deuterium. Now, obviously, tritium is a very different monster to take care of it, so we cannot do the tritium in our setup. We use deuterium as the surrogate for the tritium there. So there is this very nice reaction with a lot of the cross-section to measure the deuterium retention in this case. So if copper damage to different damage level, same damage level at a different temperature, we can kind of see the deuterium retention drops because the temperature does reduce the damage level and quite a bit from this perspective. But this change was not observed in the thermal conductivity part of it, but it was able to be picked up by the retention part of it. And when I say that helium was pretty bad to affect the mechanical property there, but helium here actually helped to prevent tritium diffusion into the deeper region. And so when you have a damage with the helium versus tungsten, and this helium damaged region, actually, you don't see much of diffusion of tritium to a deeper region there. So that's one advantage to there. All right, another thing, obviously, DTU product is the tritium and the neutron. Neutron is come to generate energy. Helium is used to self-heating the plasma. But in the end, those helium will get to the wall, first wall. Now, study has shown that depending on what's the energy of the helium, depending on what's the temperature of their wall, depending on what's the accumulation of the helium, flumes, you're going to generate a very strange microstructure on the surface of the beautiful tungsten you start with. And some of those actually looks like a herring, just grow on the surface of your tungsten, and it looks like this. You can imagine if those things break off, send it back to the core plasma, they're going to cause the instability of that plasma because it's so heavy and absorb a lot of energy from plasma there. So there is a bigger concern. This is not unique to the tungsten. It happens to the many metals. Now, the root cause of that is just many materials, including metals, the alloys, just have no solubility for the helium. Helium just does not have a solid solution with them. So we cannot change the plasma part of the spectrum. So when we were thinking about it, that we needed to do some different material science trying to accommodate this helium flux effect here. So idea is that we're going to purposely produce some microstructure in the material which actually has some pathways for the helium to release when it's being irradiated or implanted there. So net flux seen by the surface of this material is going to be reduced. Hopefully that's going to reduce the fuzz formation. So basically, we want this. We don't want that. We don't want destructive, discharge of water or the helium. So you can actually doing that. PVD has been mentioned this morning many times. We will use the PVD sputtering setup, and the purpose they change the position energy, the power, and also temperature. You can actually change the economic structure size, the green size, and to form a different type of texture here. And one of the texture, once you have those, you do a very high fluence of helium implantation to look at where the helium end up, see if you're going to see a crack there. So in the tungsten, bulk tungsten, we see crack already in that region. But for the other three films, we did not. We see many bubbles, but not crack yet. Then we subject one of those good ones to the plasma exposure. And this was done in the UCSD Pisces facility there. You start to see this hearing structure form, fuzz form, as a function of the irradiation dose there. However, if you look at the comparison between this nano-channel tungsten versus the bulk tungsten, we actually delay this fuzz formation quite significantly. Whenever the minimum fluence required to initiate the fuzz process versus the fuzz growth rate has been changed there. And in recent years, high entropy alloy has got a lot of attention, especially high refractory high entropy alloys. People were trying to find the tungsten-based alloys to deal with the issues which pure tungsten has. And so this is work we did in Los Alamos through the PVD again. You can to do a many elements system there. It's a single phase BCC system there, and then you can change the transition temperature from order to disorder. In the end, you increase the radiation tolerance for this material. Similar to the nano-channel tungsten, we were able to make a nano-channel HEA. And this is actually further reduce the fuzz formation process and compare with the nano-channel and the tungsten case there. Even with the amorphous structure, this is not the high entropy alloy, but this is just amorphous element together. You can also delay that process as well. So quickly, so far all the experiment has been done ex situ. We do the irradiation, we send the sample to other places to do the plasma exposure, then we get a sample back to do the analysis. And there are many issues happening during that cycling process there. You have to vent your chamber, change the temperature, surface contamination. Also, some of the short-lived defects may not survive during that process. So it not capture the whole picture there. So we're in the process this has been actually, predicted by the cluster dynamic simulation to reveal to you, even on the minutes, second time frame, those defects still change. And so we're in the process to set up the coupled plasma onto the ion beam facility to look into the dynamics of this tritium retention process there. At the same time, we're also set up the positron setup on our laboratory, try and look into very tiny defects like 0.1, 0.2 dPa type defects, which are very difficult to see with TEM. Because TEM is another technique people look into the damage, the production there. But anything less than 0.5 dPa, defects are so small, TEM is unable to see it. So positron is a very sensitive technique. You can look into up to 10 to the minus 7 dPa. So we're in the process to do that. And in summary, I hope I have shown you that fusion energies face still tremendous challenges, but there's opportunity seems to be brighter this time because their industries are very, into it. We need to put a lot of, the fund into it. The ion beam has been around for many years, but possesses this unique advantage to address some of the fusion materials RD issues, including radiation damage, including the analysis of helium and hydrogen. With that, I want to acknowledge my staff in Los Alamos and some collaborators that I have on this project and some of the funding source from EFRC, from ARPA-E, and the Laboratory Direct Research funding. Thank you very much for your attention. Just speak loud if you have any questions.
I've got a quick question. I wonder, I don't know so much about ion beams, but it seems that there's a separation between a plain sort of ion beam that might have multiple charges and multiple depths that it would go to versus kind of a filtered, mass filtered ion beam that goes, it's one specific charge, it goes to one specific depth.
Yeah.
Are you just mainly concerned about the maximum energy? So can you take a full, a multiple charged ion beam to do this, a simpler ion beam to do this sort of testing, and just worry about the maximum depth?
Yes, you're right. There's a plasma ion beam, I guess we don't call it implantation, but to the exposure set up there, you have multiple ion species, so you don't select that, you just dump all onto the surface to make the modification there. But here it's more, obviously we're doing much more controlled. We want to know exactly, what is the mass of the ion, what is the energy of the ion, and what is the flux of the ion. So when we do the modeling, we can compare some of those specs with what modeling person wants to put into the code there. And so it's not, this is dump everything together type setup. But obviously, this is a night sight of a way you can only see where you can see it. But plasma has its own advantage. You can expose, irregular shapes and simultaneously get exposed there. So we focus more on the fundamental side with the ion beam, monoenergetic ion beam. So when I mentioned those are three different accelerators trying to focus on same spot size, but with different energy, different species, different flux. Yeah. Thank you. Yes, definitely. We are actually looking forward to have some industry users. So only the deliverable we have for those DOG type facilities is obviously open source publications, and whenever impact for the industry product, it's a little bit different matrix to evaluate, and the industry can access for free, then which means whenever the findings need to be reported to the open source, but if they want to have a different agreement, pay a full cost, we can also do that. Now you don't need to have a peer review process there. Yeah. In fact, actually starting next month, March 1st to March 31st is our spring open call time. But you're encouraged to contact the center scientists if you want to access. Ion beam facility in the center is the only one in the 5 nanoscience centers. And obviously there are some other ion beam facilities in the Idaho National Lab for the fission research, but not for the fusion. But we're the only one for the nanoscience centers. Happy to chat after this session if anybody wants to have more information on that. All right, thank you.
So the next talk of this session is on semiconductor cleaning strategies for fusion energy. This is by Christopher. He obtained his bachelor's and master's from Leuven, KU Leuven, and currently he's a business development manager at Wacom in Germany, correct? Yes. All right.
Thank you very much.
Just stay close to mic.
Yep.
So we can hold it.
Hey, good afternoon. So thank you very much for the introduction and for the invitation. This presentation is not my work, but of a few of my colleagues that couldn't make it here today, and they've asked me to give this presentation on their behalf. So if there are, I know most of what's going on, but some specifics I'll need to refer to my colleagues, which I'll gladly put you in touch with. So I'll start with a brief introduction of the company itself, Wacom. It's a family-owned business in the very close to Jena. Jena being, of course, famous for a couple of founding fathers of the optics industry, like Abbe, Zeiss, and Schott. A lot of companies will probably ring a bell for a couple of you. And that's also where we are located. We have a production close by in Groß-Lübbichau. And we have offices in Belgium, that's where I live, and Naples, Florida, Reno, Nevada, and right now we're expanding and building a cleaning facility and eventually a production in Lewistown, Montana. So a little bit more on Wacom, very short. Basically, we combine high purity mechanical production and parts cleaning, and we bring that tech and know-how of producing and cleaning. We bring that together to ensure that parts can be produced capable for any and all requirements regarding cleanliness and mechanics. So when I bring that in focus for fusion, this is also something that's new for us, so we'll be very happy to hear any feedback on the importance and challenges that you are facing in either the research or the operation of let's say, fusion reactors and the required cleanliness. So first I'll take a step back and talk about what high purity actually means, right? So it means clean, but what is clean? That's something that's always a little hard to grasp. So that's why we use a simple comparison. So basically, when we talk about filmic contamination, what we usually refer to is German companies. So we have beer and football, or soccer. 2 beer glasses full, the German ones, or the American ones as well, half liters. You pour that onto the football field. That's what we would call, let's say, quick and dirty vacuum. So that's sort of oil and grease free. That's that equivalent. And then if you really talk about ultra clean vacuum, those 2 beer glasses, they get droplets, 2 drops on an entire football field. That's what we call ultra clean vacuum. So that's a huge difference. Just to frame it for you, ultra clean vacuum usually takes place anywhere between 10 to the minus 3 to 10 to the minus 7 millibar, where the pressures are mainly driven by desorption, being waters and hydrocarbons. And then, as we're talking about ultra clean, we need to remove those hydrocarbons, and we just have to ensure that it's only water that we're talking about. Then if we move further and go to ultra high and extreme high vacuum, the fusion also becomes critical, and we have to think about that as well. Now, when we look as a manufacturer and we have OEMs coming to us for either production or R&D, they have some requirements on assemblies or vacuum chambers that need to be made, right? So you talk about geometric dimensions, the materials that can be used, the interfaces towards the vacuum, temperature distributions that we need to think about, shieldings, stability, vibrations, and of course, as a company that specializes in vacuum, our basic vacuum requirements and costs. And what they ask of us is just to make it work again and again and again. Now, if we take that and we apply that to fusion, and we focus on the key vacuum requirements, We're talking about, selecting load outgassing materials, making sure that you select the right materials, the right surface treatments, that you have your right heat resistance, compliance with atomic safety. Like we heard before, wall conditioning and contamination control are critical. Your plasma-facing materials need to resist erosion and, need to make sure that they don't generate impurities. You need to surround that with a robust vacuum pumping system. Make sure that your radiation and magnetic fields are mapped out and taken into account. And then, of course, as you're talking about a vacuum system, you need to ensure that it's structurally the structural integrity is there and that you can prevent leaks when it's operating. And yeah, of course, instead of making it work again and again, this is fusion, so just making it work will be great. So what are the effects of heavy hydrocarbons on nuclear fusion? So you have your hydrocarbons that are introduced either through the materials or processes. These get irradiated with high energy plasma, breaks it down into hydrogen and carbon atoms. And these then, of course, can contaminate the plasma, leading to plasma cooling through Bremsstrahlung, by the carbon atoms, or it's called breaking radiation, which then cools the plasma. It will get you will get fuel dilution as well. Carbon and other particles will reduce the density of your fuel mixture, lowering the overall efficiency. Your tritium retention also is a critical issue, because carbon and hydrocarbons can chemically bind tritium, reducing the availability as a fusion fuel, of course, which you want to avoid. This increases your operational challenges. And then we have erosion and material damage. In this case, the hydrocarbons aren't necessarily introduced from a foreign source, but perhaps form with carbon-based wall materials, for example. And this erosion, reduces the lifespan of your reactor components. It introduces challenges towards maintenance. And also, this carbon that's eroded or introduced into your system will get deposited somewhere else, leading to unwanted storage of, for example, tritium somewhere where you don't expect it. Now, because we're in Silicon Valley, I decided to use AI to describe the effects of heavy hydrocarbons on nuclear fusion, and this is what he gave me, so I think we're safe for a while still. When I bring this back towards the standpoint of the OEMs and producing components that are clean and ready for ultra clean vacuum, normally what we do is, in a regular process flow, you have your raw material, you machine it, you join it, you assemble it, you put into operation. Now, if you do this, your vacuum quality will be poor. You will get all sorts of effects from contamination in particles. You get welding defects, coating defects, delamination. As a company focused also on the semiconductor industry, you will get a lot of imaging issues in your optical systems, but it will also limit lifetime and sensitivity of, for example, quantum sensors. When you're looking at E-beam and ion beam technologies, perhaps you get image darkening, and overall a negative influence on your measured values. So, in order to avoid that contamination, you need to counterbalance that. Now you have your welding fillers, cooling lubricants, the initial contamination of the raw material you're using, that needs to be balanced by something. So, what is that? That I will tell you. Basically, when you think about high purity vacuum components, you don't only have to think about making them, but you need to think about the design, the planning, then the proving, the mounting, and the keeping clean of your components. So basically, when we take that image that I showed you before of your raw material, your machining, your joining, and your assembly phase, you need to add steps to that to ensure that you can manufacture clean. That starts with the design phase. You need vacuum suitable materials, coatings. You need to think about your welding steps. You need to think about your geometry. Don't have blind holes there, for example. And then, of course, after your machining, you need to go into your cleaning, right? You need to clean the parts. That can be spray cleaning, ultrasonic cleaning, vacuum bakeouts, plasma cleaning, manual cleaning as well. Then you have to assemble all that together, also in clean room conditions, package them accordingly to keep them clean. And then, of course, when you're talking about your system, maybe you need to get an in situ bakeout of your system. You need to have run-ins or beam scrubbing, for example, to ensure that these are all ready to be used. So that's reimagining the way that production runs. So when you know what the cleanliness requirements are for your system, this cleanliness requirements, they drive your mechanical requirements, and that means that you need to design, plan, and make your mechanical parts with the cleanliness requirement in mind. So depending on the contamination levels that you have, you need to ensure that you design, plan, make, proof, and keep your parts clean. When we think about designing clean, I'll just go through the basics. I think everyone here probably knows very well what I will be talking about. You have an ultimate pressure of a vacuum system that's driven by pumping speed, conductance, leakages, permeation, virtual leaks, and outgassing. And you count all that up together and you get your effective end pressure, right? So there are a couple of knobs you can turn in your design when you're designing for a vacuum system. But of course you hit some limits, for example, when you're outgassing budgets. And this is where we can come in as well. We take those outgassing budgets into account, and depending on your application, we will assign them a certain purity class, right? So they range from class S, which is basically free of oil and grease. Those are the two beers that I talked about at the start, all the way to our PC5, which are the 2 droplets. Then, when you're making your design, what materials you put in are critical, of course, because if you, for example, put an MBR O-ring, you will get a mass spec or an RGA spectrum that looks like this, which may or may not be a problem for your application, right? So you need to make sure that you introduce the right materials. So, for example, instead of an MBR O-ring or an FKM O-ring, you go for full metal seals. Then once you've designed and have in mind what parts, how your parts look like, how they're designed, the materials that they're going to be using, you need to make those components. And making components clean is not something that's just done by any machine shop. Go in there, have it made. No, you need to control a lot of stuff, the cutting fluids that you use, how quickly you're processing. Then when you weld, how you do welding, how you treat your parts afterwards. Any contamination that you can avoid when you're producing your part will only benefit the cleaning that you have to do on the part afterwards. And basically, a part that is heavily contaminated throughout its production steps can never reach the highest cleanliness level that may be required for your application. So, for example, if you look at contaminations that can impact your welds, you get stuff like this, which are virtual leaks, will basically outgas forever and ever and ever. So once that part is produced clean, you can talk about actually bringing that part into our cleaning streets and continue cleaning them to make them ready for ultra clean vacuum applications. But in order to bring a part into a cleaning street, to think about how do we clean this part, we need to know what that part looks like before it enters. So you need to know what are the initial conditions of the parts. What's the initial contamination? What type of contamination can you expect? How much of it can you expect? And then that, together with the ultimate cleanliness requirements, drives the cleaning strategies that you will be using. So you also need geometry, weight, dimensions. Of course, these also affect how you treat the parts, and then the material and the coating on the parts are critical. Are there any no-touch areas? Is it very very fragile? Again, this is something you need to take into account when you're planning your cleaning strategy. At Vacom, what we do is we develop standard cleaning processes depending on the components, the materials and the coatings, the complexity and the size, right? So what you see here is what we have, all the materials and the coatings that we've developed standard cleaning processes for. Those are the dark blue ones. And then you see you have a couple of light blue components as well, which means that they are processable at our facility, but that we don't, that we need a dedicated look before being able to process them. So perhaps they need a dedicated custom process, or maybe we need to ensure that they need to follow a different standard process to process them. And there are a couple of materials which are just a no-go. They are not allowed into the clean room. They're just simply too dirty and will contaminate an entire clean room or entire process, meaning we need to shut down. So when you talk about making a part clean, you have different techniques that can be used depending on the contamination level of the parts and the intended cleaning specification, right? So if a part comes in that is highly contaminated, we need pre-cleaning, maybe a spray cleaning, ultrasonic baths, or solvent cleaning in order to get rid of that initial contamination. Then after that, we move on to critical cleaning that can be done through ultrasonics again, or a cyclic nucleation, high pressure spray cleaning, or even manual cleaning steps as well. And then if you go into the ultra critical cleaning, that's where you need vacuum bakeout. You use maybe plasma treatments, ozone or CO2 snow jets to really get rid of the last bit of contamination. So basically, if you look at it, it's an exponential curve. The effort increases and it increases, and the contamination that you get rid of is smaller and smaller and smaller. So great, we've made the part clean, but you need to prove it as well. Otherwise, what are you doing? So for this, we have particles and filmic contaminations or specifications, which we use different parameters, different test methods for. So we have a particle counter, for example, a liquid particle counter, or a PMC test is like a particle measurement card. For filmic contamination, you think about bright light, black light inspection, and RGA analysis. And RGA analysis is really a quantitative analysis which will actually give you information on the type of contamination that's left on your system. You can use it as a sort of a troubleshooting if you're having issues with contamination of your assemblies, for example. You can use RGA to think about where that contamination comes from. When we think about RGA measurements, we have a couple of different methods that we use that depends on the components itself, right? So we have the so-called throughput method, which is a continuous measurement technique, right? You're pumping down continuously, you're measuring continuously. The spectrum that you get in your RGA is dominated by surface adsorbents, mainly water and hydrocarbons. The only problem with this technique is if you have very small samples or very clean samples, you can't actually detect anything in your RGA system because it will just disappear in the background of your chamber, right? So your chamber, you would first measure your empty chamber. That gives you a background measurement. Then you put the part in, and then you can deduct the two spectra from each other, gives you the contamination on your part. So if the parts are too small, we use something called the accumulation method, where we will enclose a part in a separate chamber, close it off, then have another reference chamber which is being pumped down, which is connected to an RGA. Then once that a certain time has passed, you can open the valve and you will see an increase in pressure in that one chamber, and you will be able to get a spectrum so you can actually see, okay, what's the contamination on this very small part. Then a different way of doing it is a so-called rate of rise measurements. We've used these for validating our aluminum chambers that we produce, our CF aluminum chambers. So basically, this is even simpler. You have your chamber, you pump them down, you close off the pump, and you just let the chamber sit there and measure the pressure increase as it's outgassing. So, no, one too fast. So here I will show you the difference in rate of rise measurements and outgassing of two chambers. One is a stainless steel chamber that was baked at 120 degrees for 24 hours. and 200 degrees for 24 hours, compared to a full aluminum chamber that's being baked out for 24 hours at 120 degrees. And then we take a look at the outgassing rates. And what you see for the first one, 24 hours at 120 degrees, that our aluminum chamber is about 2 orders magnitude better in outgassing compared to the stainless steel version. And then even if you bake that stainless steel for the full 24 hours at 200 degrees, it improves marginally, but your aluminum chamber gives a much much better performance. Now, when you're proving cleanliness, we talked about particle counters, RGA measurements, white light, black light, but a lot of it is in process control. You want a stable, you want a reproducible process. It identify and control the relevant parameters that are important for cleanliness, and we use statistical process control to keep everything in check, right? This is basically where a lot of the secret sauce comes into play in cleaning the components. And this is not something I'm an expert in, so I'll have to default and not go too deep into this, unfortunately. Now, once you have cleaned your parts, the next step is keeping it clean, and that's where packaging comes in. So selecting the correct packaging material is very important to avoid recontamination. You need to package in a clean room environment. And the type of packaging is very important because this can also recontaminate the part. And a lot of the know-how is also in how to handle the parts, right? You have to open the packages itself, again, in a clean room environment, maybe a gray area. No touching, of course, only with gloves. And the most important part is not to talk to your components, right? You just keep your mouth shut, because just opening your mouth is a crazy particle shower that will lead to issues with cleanliness, yeah. So to bring it all back, basically we produce, we weld, then clean and assemble, and we need to control each and every step of that process. Think about the design for cleanliness in order to find a final assembly that is up to spec to what you want your customer to have. What we believe is that the know-how and lessons that we learned from the semiconductor industry can also be used in fusion research, the R&D labs, etc., that require pristine conditions for plasma integrity, for example, or for imaging. You want to prevent unwanted impurities, can disrupt any of the reactions or measurements that you have ongoing. And by adopting a lot of the best practices that were developed for the semiconductor industries, high purity materials, ultra clean processing techniques, contamination-free assembly, environmental monitoring, I think also the fusion research in general can really benefit from this, enhance its efficiency and safety as well, minimizing a lot of the detrimental effects of impurities and hydrocarbons in your vacuum reactors in general. And with that, I will end this talk, and if you have any questions, I think we have some time left, so feel free to ask, and if you think about them afterwards, we're exhibiting here with another colleague as well, so please feel free to stop by and come talk to us. Yeah, thank you. Hi. So I think you're talking about, let me just move this one, right? The liquid particle counter? Yeah, so again, I'm not an expert, but the way it works is you have your components, right? And then the particles that are on your component are transferred to a liquid, and then I think with light scattering, you can count the amount of particles that are detected, and then you can bring that back to whatever your requirements are on what the particle counters are.
All right. So the last talk of this session is by Dr. Carlos Guerra. He obtained his PhD from ETH Zurich and also conducted his research at EMPA. It's a national lab facility there. And he's a co-founder and CEO of Swiss Cluster. And he's the last person standing between us and happy hour. So let's hear Dr. Carlos.
Is there a changer or something? Do you have a light?
No, I don't. You just use, stay close to mic. So
Okay.
they're recording you
I see.
on this. Yeah, you can flip.
All right.
Yeah, there you go. Okay. Just try to stay close to
All right. Thank you very much. And thank you for the invitation. Thank you for staying here before happy hour. I'll try to make it fun. So yes, I would like to present today a little bit about our company and show you a few examples of the type of materials that we do in our equipment using both atomic layer deposition and physical vapor deposition, or ALD and PVD. My name is Carlos. I'm the co-founder and CEO of Swiss Cluster. We're a young company. We're based in central Switzerland in a small town called Spitz. So we're in a very privileged location, a very nice setting to do coating activities. We're just at the edge of the Lake of Thun and just in front of the Alps. So we are a spin-off of EMPA, so the Federal Laboratories of Material Science in Switzerland. We are founded in November 2020, so just a little bit over 4 years. And we're 70 employees, we're growing, and yeah, you're welcome to visit us anytime. So what do we do? So in these years, we have already compiled our product portfolio. So this is the equipment that we offer for both R&D and small batch, and also for production. So for the R&D, we have the SE Cube. This is a standalone batch ALD system. And the unique of this type of equipment is that we can tailor the dimensions of the chamber so that we can fit particular geometries, different sizes, or that we can also target different production volumes. We can go from wafer all the way to 70 liters. Then on the next one, we have the SE1, which is the first system that combines ALD and PVD in a very compact and modular equipment. This is our flagship product. I will talk a little bit about this system in a while. Then for the production part, we have the SE Optima. So for this one, we really scale batch ALD from 70 liters all the way to 1,000 liters. So this is for really larger production volumes or larger parts. So we tailor these dimensions. We work with the customer to make the part to fit the production volumes that are required. And in our roadmap is to scale the SE1, which is a wafer-based system, to batch ALD and PVD. So yes, today I will discuss a little bit about the ALD PVD system, the SE1 series or cluster system. So by now, many of you are familiar with the cluster systems, right? So these are essential equipment for the microfabrication of many of the devices that we know today. So where we move the wafer between chamber to chamber, and we can do ALD, PVD, among other processes. However, this type of equipment, it's quite inaccessible for many researchers or for people to do also research doing this type of technology without breaking vacuum and without moving the sample. The alternative for R&D is then a customized system where you just plug in your PVD chamber, you have a gate valve, and then you have your ALD chamber, and then you move your wafer between substrates, and yeah, it's often not the most repeatable process, right? So what we came up with is to make this type of combination in a much more compact system, in a very modular system, so that we can do R&D for all of these type of combination. So how the system works is we have in the top chamber, we have an ALD chamber where we can do thermal ALD or plasma enhanced ALD, accessing different materials library from all of the ALD that can offer. And then underneath, it's a PVD chamber, which is divided in with a gate valve, where we can do sputtering or evaporation. So when we have the gate valve closed, then we can do an ALD process. We open the gate valve, and then we can sputter through the gate valve, and we can do this literally hundreds of times to create different types of multi-layer systems. So, of course, the first system, when we created this first machine back in 2020, the first system that we wanted to, the first model material system that we wanted to create was aluminum and aluminum oxide. So we sputtered 20 nanometers of aluminum with magnetron sputtering, of course. And then every 20 nanometers, then we deposit 1 nanometer of aluminum oxide by atomic layer deposition. And then we do this hundreds of times until we have a 2-micron thick film. You can see this a little bit more clearly. You can see that effectively by introducing these ALD films every 20 nanometers, we effectively break the grain growth of the metal film. So we can really have a very systematic periodicity of 20 nanometer grain size of aluminum, right? So this really resembles like a brick and mortar structure. This is a cross-section TM image. So when we do mechanical testing for this type of microstructure, we see that it has 6 times the hardness of just pure aluminum, so 2 times harder than the strongest aluminum alloy. So this type of combination of material can increase the mechanical performance of the coating of just pure aluminum. Similarly, we anneal this type of coating, in which we go from room temperature all the way to close to the melting temperature of aluminum. So in this case, 520 degrees. And you can see from the EBSD images the grain size distribution, and as we go to 520 degrees, the ALD layers act as a thermal barrier layer, so it prevents the grain growth across the vertical direction and minimizing the grain growth along the. Thanks. Is it better? So the ALD layer also minimizes the grain growth at the lateral direction, right? And because we can retain this microstructure at these high temperatures, we can have 50% of the mechanical performance of the original coating, right? So this type of strategy can improve the operating temperature of existing coatings. So our partners at TEMPA, they continue also investigating this grain growth mechanism in different types of coatings. So for instance, in this one also aluminum nickel alloy, going from the as deposited, where you can see really the multi-layer structure in the TM images and with the ESD. And as we go at higher temperatures, then you just have this very lateral grain growth, right? And depending on the material, depending on the thickness, of course, you can also tailor this type of effect. Similarly, doing the hardness testing, then we can observe how this type of effect affects the mechanical performance. Another interesting application of combining ALD and PVD is the fabrication of stable meta surfaces. So in this work, what we did is depositing the electric layer, metal oxide by ALD. So this is the aluminum oxide, popular aluminum oxide. Then we deposit a metal layer between 10 to 30 nanometers. And then what we do is a heat treatment that dewets the metal film to create these nanoparticles of very defined sizes and density distribution. We can repeat this several times so that we can create this multi-layer structure of meta surfaces for plasmonic effect. So you can see that going from one layer 2 layers to 3 layers. We measure the optical response of these type of structures, going from a broad spectrum for 1 layer, going to a much narrower spectrum for 3 layers, and also reducing the reflection. So we can do this for having different types of layers in which we maintain the constant nanoparticle size. And then we measure we observe the diffuse illumination and the direct illumination so that we can tailor this optical performance. And we can do this also by varying the nanoparticle size in different layers. So we can do this all in the same system in just one-step approach. So with this type of approach, we can spatially distribute or tailor the spatial distribution of the nanoparticles, the nanoparticle size, by tailoring the thickness of the interlayer of this aluminum oxide, but also by increasing or decreasing the particle size in all of the different directions. So we observed that most of the properties that we can obtain combining this multi-layer system is increasing the temperature, the thermal behavior, and the mechanical behavior, right? So we always wanted to understand what was the effect of each of introducing ALD layers, whether if it was because of having a grain size refinement or was it because of introducing an ALD layer, right? So we know that metal multilayers or metal ceramic multilayers, mainly deposited by PVD, they have an effect of increasing the hardness by decreasing the layer thickness of the multi-layer system. Since this was mainly for PVD layers, right? So we had to do our own work to discriminate whether the grain size or the ALD layers are the main responsible for contributing to this increase in mechanical response, right? So our scientist, Amit Sharma, he devised an experiment to discriminate or to decouple these two effects. So he deposited pure copper, right? So you can see the large grains in these nanomega images, and adding aluminum from 2% to 12%, you can see how this has a grain size refinement independent of the addition of the ALD layers, right? So you can see the aluminum oxide also in between, separating the different multi-layers, but the grain size remains the same just because of this solid solution. We also do the annealing to assess the reliability of the film at higher temperatures. So we see that still at 600 degrees, we have this prevention of the grain growth because of the ALD layer, right? So we take the copper aluminum 5%, and every 120 nanometers, we introduce 2 nanometers of aluminum oxide deposited by ALD. You can see how the aluminum oxide by ALD really conforms along all of the surfaces of every PVD layer. So this passivates surface defects and provides this glue to maintain the mechanical reliability. So if we do this every 120 nanometers for 3 microns, then we have 25 bilayers. When we do this every 60 nanometers, then we can obtain 50 bilayers, right? But still maintaining the same grain size distribution along the cross-section of the material. And then we do this for 30 nanometers to create 100 bilayers, right? So in this way, again, we maintain the same grain size distribution, but we just increase the number of interlayers of ALD. We do then mechanical compression, so pillar compression. We mill out these pillars of defined sizes, and in situ in the SEM, we do this pillar compression. You can see the effects. So this is the yield strength, measuring the yield strength of pure copper, and how, as we add aluminum, naturally we have the solid solution strengthening. So keeping up with theory. And then when we introduce aluminum oxide for just pure copper every 60 nanometers, so having 50 bilayer, then we see how this effect, this strengthening effect, is due to the Hall-Page effect, but only because of the interlayer addition. So it's not really because of any grain size refinement, as in the other example, but really because of introducing these ALD layers, right? Then we take the copper aluminum 5%. We do the 25, 50, and 100 bilayer, and we see how this increases the yield strength of the material. So this is a scaling effect due to the grain size refinement of the copper aluminum 5%, but there's a significant increase because of adding aluminum oxide. So really showing that the responsible of this high increase in the mechanical behavior is due to the addition of the ALD films, right? And we see this scaling effect also with the copper aluminum 10%. So this becomes a good strategy not only to increase the mechanical behavior, the yield strength of the material, but also we can increase the ductility of this type of material. And I will show another last example. So going towards more exotic materials, we also work with high entropy alloys. This is an iron, cobalt, chromium, nickel, which yields an FCC coating material all the way to 3 microns. And if we add aluminum, then this turns to BCC, same composition. And then we do the same. We do a 50 nanometer bilayer composition of FCC, BCC, without and with the introduction of 2 nanometers of aluminum oxide by ALD. And when we do our micropillar compression again, you can see in the blue column the FCC material, just pure FCC, this high entropy alloy, how it behaves, the yield strength that it has, but then when it breaks, then it breaks in a very brittle behavior. The BCC only system, then it has a slightly higher yield strength, but then it has also a very brittle behavior. When we do the combination of FCC, BCC, there is a dramatic increase for the multi-layering system, but we still have this very brittle fracture. When we introduce the ALD layers also every 50 nanometers between this FCC and BCC, then we see that the microphone falls. It's already exhausted. I think it works. Perfect. So yes, with the combination or the introduction of these aluminum oxide layers, we see that there is not only an increase in the yield strength of the material, but there's also this very nice effect, which is just having a very plastic deformation. So this is a way to obtain a very hard material that has a very plastic behavior, right? So this already in a zoom-in TM image of the post-mortem pillar, we see that there's no crack in this pillar, right? So we really have a very plastic effect in this type of systems. We, of course, also tried with just BCC. We obtained probably one of the hardest metal, which is also very plastically of 6.5 gigapascal. So this is actually quite high. And if we put all together all of the material combinations that we have done in this type of system, in one-step process, in our SE1, we see that in the Ashby plot, we are already above of what has been reported in literature of this type of material chemistry. So yeah, I hope that with this few examples, I was able to show that ALD and PVD has a very nice effect that can be used for different applications. And yeah, we're happy to kick off this more strict discipline of combining ALD and PVD. So yeah, with this, I want to thank also our colleagues back in Swiss Cluster and all of our funding agencies and you for your attention. And yeah, if you have any question, let me know. Just in time. Yeah. Yes, that's a good question, and often a question that we get. So typically when we deposit ALD, basically I will go back to the, you already down-react all of your gases, right? So it already deposits an aluminum oxide, which actually aluminum oxide, it's a great barrier layer for preventing the desorption of water molecules. So you're already passivating your chamber. Once the ALD process is finished, you down-react all of the gases. There is, of course, a pressure difference between the two processes. So the ALD has its own vacuum system working at background pressure -3 millibar, right? And the PVD, we have it at -7 millibar. We can already open the gate valve at this difference of pressure, but we always just introduce a little bit of gas. So to equilibrate to -3 and -3 millibar, we open, and it takes a couple of minutes to go back to background pressure and then start your sputtering. So we measure with time of flight mass spectrometer, and we didn't see any residual gas from the ALD into the PVD chamber. Because of this thing, you already down-react your gases. Of course, you might be thinking, well, if you do 500 nanometers of ALD, you have this accumulation of water, and yeah, it takes much longer to pump. But typically, since we're doing just a couple of nanometers, even 100 nanometers, the accumulation is not so high. Yes, it's a worm wall reactor. It goes to 150. It's an aluminum chamber. It makes it easy to maintain and to replace. So you don't have so much downtime, and also it's less expensive to replace for the customer. 150 degrees on the chamber walls, but on the stage we can go to 800 degrees using a special stage. Yeah. Yes. Yes, that's a good question. So at this point, we try to focus only on flat wafers, flat substrates, for having this proof of concept of the combination to test. But our goal is to go towards complex geometry so that we can still do the same combination, of course using the same strategies that PVD community uses with carousels and rotation, and then you can minimize this shadowing effect from the line of sight. So right now it's only for flat wafers, but we have in our roadmap to go to patch and 3D parts. Yeah. Thank you. We're open for business. Yeah. So what's the difference between doing a multi-layer just by sputtering? That was the question that I was waiting for. So of course, because you can do aluminum oxide or you can do any other oxide by reactive sputtering, right? But then when you do this, you're introducing oxygen, and the aluminum oxide, for instance, if you're doing on aluminum, it will continue the same microstructure, the same columnar growth. It will still be full of defects as PVD grows, right? So that's where ALD shines, because you really have a pinhole-free film that conforms over the whole surface and really breaks this grain growth. Yeah. Yeah. It's totally possible. So there's always an application for both things. The thing where maybe PVD will have a bit of a problem will be on more complex shapes. So when you have also the addition of ALD layer, then you can really conform on that part. You also have different access to different materials that probably PVD has a little bit of a challenge. And it really depends on the application, right? Often to have the same effect that you get with ALD, for instance, for anti-corrosion with an aluminum oxide layer of 20 to 50 nanometers, you probably need a thicker layer of PVD to get the same effect. And in this case, then you have probably a thinner layer. You just require a thinner layer in order to get the same effect. Yeah? Please? We would love to try, and we're trying. We have done titanium nitride multi-layers. Still not published or still in process. We're doing this, but there was still so much to do with just aluminum oxide, because it was the first time that we were doing this, that we just had more questions and more questions that we wanted to understand and to see how the system behaves. And aluminum oxide, it's just a model material that it's easy to replicate. But it would be possible to use titanium nitride, zinc oxide, titanium oxide, and have this combination also with other type of materials from the PVD library. Interestingly, because you have this possibility to do amorphous layers or crystalline layers with ALD, then it also opens another type of knobs that you can turn to do this tailoring, right? So that's the effect. Yes, good question. So one of the advantages in this case in our system, because we have the substrate fixed on the stage, we don't have to move it between chamber to chamber. We can keep an homogeneous temperature from start to end. We can also control if we want to cool down in between, or we can or heat up a little bit more, but that also has an advantage to do this type of processes without having to cool down and heat up again. Having also the stage in the same chamber gives you access for metrology tools to have one point access to do the metrology of the ALD and the PVD process in the same point. So you don't have two systems, right? Mm-hmm. So you can do in situ? Yes, we have lots of in situ metrology that we can do, one of which is to measure in situ the stress as you're depositing your material. So there is a, I don't know if you see it from here, but there's a laser on the bottom where we can introduce and we just measure the deflection of the wafer as we're depositing or heating up. We have introduced time of flight mass spectrometer, QCM, ellipsometer, and so on. Yeah, because you have direct access to the chamber, then it makes it very easy to do this. Yes, we have 2 patents for the integration and for the process. Well, 3 patents now for this type of integration, and another patent for the other systems. Sorry, what? So you have the MOS in situ MOS system built in there? No, it's not built in. We integrated from our partners to the system, so we work together to make the integration the seamless way possible, and of course in the future to access this data and have an intelligent system where you can have commands based on the stress that you're measuring, the gases that you're measuring, and so on. That's in the, yeah? So you see the way how compact the system, I just wondering how difficult it would be if I were to incorporate, say, EQP. What, sorry? To do plasma enhance? Well, it's just that I'm not listening properly. So it's the plasma diagnostic. Yes, of course. So inside the chamber, we have introduced a Langmuir probe so that you can measure in different positions. If you see it here, actually, there's a microwave plasma source to the left-hand side. So we position them around the chamber so that we can have access from this microwave plasma along the wafer. So we measure with Langmuir probe the plasma environment with different parameters and so on. Or we can also use a quantum device also from our partners where we can measure ions and neutrals as well. It's very easy to integrate a flange into one of these panels that you see there, and then just have access to the inside the chamber. So yeah, at some point we also had the same questions as users, right? We were users of this type of equipment. So we always wanted something that we can always continue upgrading, continue adding, and having this non-restrictive original design that we can always continue upgrading and improving. Yeah. Yeah. Yes, we're almost towards the end. I think it's booth 13. Please come and talk to us, and yeah, we'll be happy to take orders. So.